Thank you. Welcome everyone, and I'm very happy to presenting this work in the CASA conference. And I will be talking about our research, which is titled as Multi-Level Tetrahedralization-Based Accelerator for Ray Tracing Animated Scenes. And note that this is a collaborative work between researchers in Bilkent University and NVIDIA. I will start with a quick outline. I will first talk about an introduction to the topic and then background and related work. And then I will describe the tetrahedralization hybrid structure for ray tracing, and then talk about the nearest hit cost heuristic that we use. And I will talk about how we can adapt this structure to the animated scenes. Then I will give experimental results and conclude the presentation. So as a quick introduction, ray tracing and visibility tests are core topic in computer graphics for many tasks. And it's basically a rendering technique to simulate the propagation of light to produce realistic images. And to do that, we often use visibility tests in order to find primitives along the path of the ray. Sometimes we search for nearest, sometimes we search for all, or sometimes we search for any kind of intersections by array to compute those interactions. And in general, the nearest tests are quite expensive to compute, and these can be speeded up using accelerators. And the famous accelerators are KD3s and bounding volume hierarchies. In this work, we propose a BVH tetrahedralization hybrid acceleration structure to speed up ray tracing, mainly the visibility tests. And then we propose a construction method for this structure. And then we show that this structure can be adapted to the dynamic scenes as well. Let me give a quick primer on acceleration structures. Acceleration structures are used to reduce the number of ray primitive tests when doing ray tracing or any kind of queries along array, basically. And the common used ones are uniform grids, KD3s, and bounding volume hierarchies. And alternatively, as we do, one can use a constraint tetrahedralization when searching for closest intersection. For the KD3s, we recursively subdivide the scene into two halves, and then those splitting planes are perpendicular to one of those axes. In the leaves, we have the primitives, and a primitive may belong to multiple leaves. And this is actually quite introduced a lot of time ago. In the KD3s, when we are doing a nearest hit traversal, we start from the root and visit each node in race order, and then test all the primitives when we are in the leaf. And this actually stops when an intersection is found. Of course, the structure of the tree affects the nearest hit performance. And in general, when we are constructing the KD3s, we use a heuristic called surface area heuristic. And this makes sure that we construct a tree so that it's efficient when we are querying for these closest intersections. And surface area heuristics generally estimates the expected nearest hit cost by assuming rays are distributed uniformly, and they originate from outside geometry. In the bounding volume hierarchies, which are actually very popular at the moment, we have a recursive partitioning of the primitives, and the nodes itself contain a bounded volume of primitives. And in the leaves, we actually store the primitives, and the bounding volumes can intersect, but we generally don't allow duplicated primitives in BVHs. When doing a nearest hit traversal, we start from the root and visit the nodes in that first order, and visit the node's children if the ray actually intersects with the bounding volume. And then we test all the primitives residing in a terminal node, and therefore we don't do any early termination. They are actually quite similar to KD3s, and similarly, the structure affects nearest hit performance. And again, they are constructed using a top-down manner using surface area heuristics. And in general, the bounding boxes, the axis-aligned bounding boxes are used as a bounding volumes, and nodes most of the time have two children, but in the recent approaches, we have 4, sometimes 8, and sometimes 16 to utilize new hardware. Actually, we can have different number of children. As an alternative, we have tetrahedralizations when doing ray tracing, and we can actually use the constraint tetrahedralizations as an acceleration structure. This interesting method is first proposed by Lngo and Dutre. However, due to the limitations of tetrahedralization algorithms, right now it only supports triangular primitives, and self-intersections are very hard to handle, so we are not allowing it, and therefore the real-world applications are quite limited. So in a basic way, we construct the constraint tetrahedralization using the scene geometry, and then we just traverse the ray along these tetrahedralizations, and when we reach some kind of geometry, you just know that our ray actually intersects with some kind of geometry. So, as I said, in the nearest seed traversal, we start from a source tetrahedron where the ray origin is actually located, and we traverse the tetrahedra one by one in race order, and we stop if a constraint phase is reached. The constraint phase here actually corresponds to the scene geometry. In the tetrahedralizations, in order to find the next tetrahedra, there are several efficient methods. Lngo and Dutre uses scalar cross product, and Maria et al. Uses Fluker coordinates. And in our previous paper, we have used projected two-dimensional coordinates for fast traversal. And we also proposed some additional compact storage schemas where we try to compress the memory required for a single tetrahedron. These numbers, TET 32, TET 20, and TET 16 are different versions of our data structure. And as you can see, they are getting smaller. These numbers correspond to the number of bytes that we use to store them. At each compaction level, they get harder to traverse because we need to encode and decode some additional information during traversal. But we also utilize, we take advantage of better cache utilization when we have a smaller footprint. And also we can render much bigger scenes because we can actually feed more geometry to the, let's say, memory. And since it is especially limited in the graphical processing units, it's quite useful. So our structure is actually a hybrid of bounding volume hierarchies plus a tetrahedralization. We call them as a BTH. And it's actually a BVH with tetrahedralizations on some of the leaves, and combines the strengths of the both structures. The structure can have self-intersections, unlike tetrahedralizations, and it can support all kinds of primitives, and we can actually benefit from early termination, which is actually a very nice point about the constraint tetrahedralizations. And the structure, of course, affects the near receipt performance. And when we are constructing the BTH, we have 3 steps. We construct the BVH first, and then we mark suitable nodes, and then we select and construct tetrahedralizations under those leaves. So the first step is to construct a complete BVH first. And for that, we use a top-down construction method and use the surface area heuristic. And in the second step, we mark self-intersection free nodes, which doesn't have any kind of intersection, basically. And then we mark the nodes from bottom to top. And a node contains self-intersection if its descendants contain self-intersection, or if its children has an intersecting primitives. And the good thing about this thing is we already constructed the BVH, so we can use that structure to speed up those self-intersection detection. So once we have BVH, we just need to decide in which nodes we need to have a tetrahedralizations. So we select the node if the cost of traversing that node is actually better than cost of traversing that node if it was like a BVH node. So we construct tetrahedralizations by children nodes and use the access-aligned bounding boxes to bound tetrahedralizations. In the nearest seed traversal, it's actually similar to the BVH traversal. We start from the root and visit the nodes. And if the node is a tetrahedralization leaf, we find first tetrahedron, and then we initiate our traversal from that tetrahedron and continue. So in order to construct efficient structures, we need to use a nearest seed cost heuristic. So as I said, when we are constructing the structure, we check whether it's actually useful to have a tetrahedralization in this structure. So we need to have an idea about the cost of that tetrahedralization when we are actually traversing it. This is quite similar to the surface area heuristic, and cost tet, meaning the cost of traversing tetrahedralization, we can actually approximate it. But when we are doing that, we need to assume that rays are distributed uniformly and they are originating from outside of tetrahedralization. So the cost of a tetrahedralization is related to the number of tetrahedra traversed. It's actually a very simple formula. We multiply the average number of tetrahedra traversed with the cost of traversing single tetrahedron, and we get an approximate cost by multiplying these numbers. And in order to approximate that value, we have three different methods. First, the sampling-based calculation, and then average step-based cost calculation, and then primitive count-based cost calculation. Sampling-based cost calculation is a very simple approach. It's a Monte Carlo approach, and we randomly sample rays, and we just count how many tetrahedra we traverse along the ray. But as you can imagine, this is quite expensive. Accuracy gets better as n increases, and with this method, we can actually approximate the true cost quite well. But we require a tetrahedralization for that, so it's not really efficient since it works by constructing the whole structure beforehand. Therefore, it's slow, but we use this to evaluate other methods we have. Our second method is average step-based cost calculation. In order to compute this, we have the average depth of rays divided by average length of the edges. And to find the average depth of rays, we can have a simple method such as having rendering an object to the screen and processing the depth buffer like Z buffer and find the average depth of rays, etc. And compared to sampling-based cost, this tends to underestimate the cost. We found that in our experiments. And our last method is primitive count-based cost calculation. A primitive count in a node can be used to approximate the actual cost, and we empirically found that cubic root of number of faces in a node is a quite good approximate of the cost of the tetrahedralization. And when it's compared to sample-based cost, we saw that this approximates the cost well. So when handling the animated scenes, for dynamic scenes, these structures need to be adapted. And we use two approaches to update. We can use two approaches to update the acceleration structures. The first one is rebuilding the whole thing, and the second is just updating where it is necessary. And there's, of course, this trade-off between build time and build quality. We can categorize the scenes, dynamic scenes, according to the type of motion, as they are having hierarchical motion and they are having an incoherent motion. And we can have different algorithms used for different types of motions. In our structure, we utilize a two-level hierarchy. So we have a bottom level acceleration structure, BLAS, and we have a top level acceleration structure. And we construct a BTH, which is a bottom level structure for each object. And then we construct a bounded volume hierarchy, which is actually a top level structure for these bottom level structures from these structures. And when doing a nearest hit traversal, we traverse the top level structure first. And when we reach a bottom level structure, we transform the rays into object's coordinates, the local coordinates, and we traverse those bottom level acceleration structure. And when seeing changes, since those bottom level structure does not change, we only rebuild the top level bounding volume hierarchy. This is our experimental setup that we used in our experiments. It's relatively a new setup. And for the ray tracing, we use a full HD resolution images. And we have a multi-threaded implementation with a tile-based renderer. We shoot a single ray per pixel, and we only trace primary rays for these experiments. And we used two versions of BTH. One is BTH20 and one is BTH32. These corresponds to our different compact schemas for traversing tetrahedralizations. And both methods rely on CTET. So when we increase the CTET, we have less tetrahedralization. When it decreases, we have more tetrahedralization. And this is to show how CTET affects the tetrahedralization levels. As you can see, when it is the number is small, the CTET is small, we get more tetrahedralizations. The colored regions are the ones that are actually tetrahedralized. And as we increase, we don't have as much tetrahedralization as before. And when selecting the cost method, we perform the grid search and we choose those average based method. And for the BTH32, we used CTET value of 0.7, and for the 20 version, we used 0.5. And these are experiments on static scenes with three different models: Armadillo, Lumberyard, and Sponza. These are the statistics for just our structure to find do a parameter search. And these are the rendering construction and rendering times for different traversal methods, comparing our method with a BVH and a KD3. And as you can see in those small scenes, our compact structure BTH20 beat other methods, although the results are quite close to each other. And in the construction times, BVHs are much, much better. And here, as our scenes get larger, KD3 gains an edge, but our structure is still competitive. And again, in the construction times, BVH is just extremely very fast. These are another set of scenes for our one of our methods from our old paper and our new methods, etc. And also comparing to BVH and KD3 as well. Results are quite similar. And these are for the animated scenes. We have a rotating armadillo, we have random motion, and we have falling hairball scenes. And again, our structure, especially the 20-byte version, is very competitive compared to the BVH, but still the construction times are nowhere close. And here's a quick video about our animations. Let me stop sharing here and show it to you. These are the dynamic scenes that we render using our hybrid approach. There's a BVH on the top, and in the bottom levels, we have constrained tetrahedralizations. I will be back to my presentation again. In conclusion, in terms of rendering times, BTH outperforms BVH in all of the scenes. All the results are quite close. And BTH outperforms tetrahedralizations in all of the scenes. And BTH is faster than KD3 in some of the scenes. When we were doing our research, we kind of observed that this structure can actually have advantages of the both versions, combining the orthogonal strengths, and can create a better structure. So this results kind of confirms that. And in terms of construction times, BVH is always faster than BTH, and BTH is always faster than tetrahedralizations, and BTH is usually faster than KD3s. And for dynamic scenes, we showed that BTH can be adapted for dynamic scenes, and two-level BTH is faster than two-level BVH. And as a future research opportunity, we would like to explore the animation of deforming geometries, because tetrahedral meshes tend to handle these kind of geometries quite well. And we also want to explore how we can exploit ray connectivity for secondary rays in this tetrahedralization structure. And thank you for listening. Let me know if you have any kind of questions, comments. Thank you.
Yeah, thank you very much for the nice presentation. So everyone, like, feel free to ask questions in the chat, the Q&A box, or just to raise your hand. I'll try to monitor that. So I guess while people are getting ready for their questions, maybe I'll ask a question myself. So I'm wondering, like, your method usually beats BVH on rendering time, but when you consider both rendering time and construction time, then BVH has an edge.
Yes.
Could you comment some more on that difference?
BVH, there are very efficient methods to construct BVH at the moment. Like the state-of-the-art methods go blazingly fast. But when we are constructing the BTH, actually, at some point, we need to first construct a rough. Actually, we need to construct first a BVH, and then in some nodes, we need to convert them to the tetrahedralizations. And actually computing or constructing those tetrahedralizations are quite expensive. I don't remember the exact complexity of the algorithm, but both, like the constant wise, both the operations involved and in both, I would say, the complexity wise, it is much costly compared to the BVH alone.
Okay. I don't see any questions, so I'll ask just a last quick question.
Sure.
Please keep it with a quick answer, because we're a little bit tight on time. So in dynamic scenes, like I saw in your videos, it was just a rigid transformation. So you mentioned that a little bit in your future work. So could you elaborate a little bit on, like, really non-rigid deformations?
The good thing about tetrahedralizations is when you are having a non-rigid, for example, some kind of deformation, maybe you can do it by using a freeform deformation box or something. And for that, for most of that kind of motions, you can just keep your tetrahedralization structure intact. The topology does not change, but just the points will be moving away. but you won't be updating the actual structure itself, like the neighboring information and etc. So if you somehow utilize this, you don't need to check anything at all for an update. You just have your tetrahedralization inside those nodes in the bottom levels, and you update your vertices, your vertex positions to account for these deformations, and you are done. Then it will be a real time, no need to change anything.
So you save a lot on reconstruction, on construction time. Okay,
Yeah.
great. So thank you very much for your nice
Thank you.
presentation.